Okay, quick announcement before we get started. So next week is week 5. So week Friday is your first midterm, Math 155. Bet you guys are all really excited about that. Try writing them, it's worse, trust me. Okay, so yeah, quick announcements about that. It's on Friday, February 3rd. I'm going to make it 45 minutes because there are a lot of you in this class. We're going to be at capacity in this room. So anything you can do to try and help make that run smoothly would be much appreciated. So please bring your ID, arrive in plenty of time. I know many of you arrive early anyway, which is great. If you could bring as little as possible into the room, that'd be much appreciated as well, just because otherwise 400 people chucking their bags down here is going to create problems. So try and bring in as little as you can. No calculators are required. So everything, all of your answers will be left in calculator ready form. What else? The types of questions are going to be mainly, the types of questions are going to be mainly similar to things that you would have met on the IQs, some of the OQ questions as well. So they're good practice, very similar to the kinds of things that we've been doing in the problem class. Okay, so if you want more practice, some of the questions in the textbook are quite helpful, but I would probably go for ones that are more on the slightly wordier end of the spectrum, as opposed to things that are purely mathematical and are distinct from the biology, if that makes sense. Okay, so we've gone through some problems, and we'll go through some today where there's not really a biological context. I'm going to be trying to place most of the exam questions in a biological context, though. So make sure you're comfortable with word problems, and also think about interpretation as well. Okay, so like I said at the start of this course, really wanted to get you guys thinking about interpretation, not just doing some maths and having that absent from the biology. Okay, so there's a question there. So we're currently writing the exam, so we're just finalizing what questions are going to be on there, and we'll have a formula sheet in there that will have all the formulas that you need, and I'll distribute that before. So you shouldn't, again, I don't want you guys spending time memorizing stuff, because that's not really a skill I think that is super valuable. I'd be much happier if you can't remember something but you know how to apply it and you see it. Okay, so no cheat sheets, but all of the things that you should need will be in there. Okay, any other questions? No. Okay, so sorry. No, so they'll be similar to the IQs and problems that we do in class. So, there'll be some word problem, and, you've got to interpret that, put it into some mathematical formulation, do a bit of an analysis on that, and then come up with some interpretation. Okay, so quite similar to the sorts of things we do here. Any other questions that I missed? Oh, sorry, at the back, yeah. So everything, good question, everything up to the first midterm is included, okay? So it's everything up to next Wednesday. Yep. I don't have a practice test. Like I said, I think the kinds of problems that we've been doing will be very similar to the ones that will be in the exams. So I would suggest going back over the problem sheet. Next Wednesday, I said it was up to next Wednesday. Next Wednesday is actually going to be a review session anyway. So the last new material will actually be on Monday of next week. So I'll go through some examples of, again, similar problems to the sorts of things you'd be expected to do on the midterm. Okay, so there should be plenty of practice between what we've done in problem classes, the self-study questions at the end of the lectures and the problem sheets as well, things that are in the textbook that are on the wordier end of the spectrum. Okay. Any more questions about the midterm? Yeah. I think we'll probably have about 3 questions, okay? So it will be about a similar length to an IQ, slightly longer. Yeah, generally what I'll do is I'll work through it and then I double my time and add a little bit, and if I can do it in 20 minutes, you guys should be able to do it in 45. It's kind of roughly the mark. So I do go through it myself and make sure that it should be doable in time. Okay. Anyone else? No. Okay. So we're moving on to a new section of the course now where we're going to be thinking about functions of multiple variables. Now, remember I said right at the start that a lot of this course is essentially taking things you already know in one variable and then thinking about them in more than one dimension, so having more than one variable, okay? And there are lots of cases where that's important. A little bit quiet, guys. So, for example, a lot of cases that you've maybe met in your real in the real world, in day-to-day lives, you've not realized are functions of multiple variables. So the example here is isotherms. So if you want to look at temperature across a map, if you've got latitude and longitude, you've got two variables there, you plug them in and you get out some value for temperature. The same can be done for things like pressure, salinity gradients, pH. There's an example in the lecture of body mass index. So you've got your mass and your height to work out your BMI. Lots of problems involve multiple variables, okay? So we need to start thinking about how we can work with functions that involve multiple variables, what that means mathematically, and how can we interpret them biologically. And this stuff will lay the foundations for going on to thinking about rates of change in more than one dimension, okay? So when we think about taking a derivative of a function of one variable, you know, you find a point if it's representing a curve, you find a point on that curve, you draw a tangent line, that gives you the gradient and then your rate of change of that function, okay? But if you've got more than one variable, we need to think about how do we do that when we can take the derivative with respect to more than one thing, okay? So with an x and a y. So that we'll get on to later this week. Today, like I said, we're just going to focus on functions. Quick show of hands who watched the pre-lecture material. Great, thank you very much. Okay, so it started off talking about a bit of notation. So this isn't going to be super notation heavy, okay, but it's worth recognizing a few of the key terms and how we write things down like this. So this is kind of saying here, this is the set of all, so those curly braces are saying the set of all values for f of xy is going to be the values xy, so pairs of xy that are in some domain D. Okay, so there's a little bit of notation here. Just make sure you're familiar with that. Like I say, we're not going to be super notation heavy though. Okay, I mentioned BMI as an example. So if you've got your mass and your height, just as with a function of one variable, you plug these values in and then you get a value out. So that's one way of representing things. We can also represent them through a chart like this. So if you've got a wind chill index, you have some actual temperature, your air temperature maybe, and then you've got wind speed. We can read off a particular value. Again, this is just the same thing. We've got a function of two variables here, but we can represent it as just a table of values. Okay, you can think of this as being, if it was a continuous surface, you've just taken samples at various points along that surface. Okay, so I mentioned that we can represent these in the form of a table, numerically. We can talk about functions verbally. We can represent them algebraically using explicit formulas. We also need to think about what they look like visually. So if we've got a function of one variable, we need two dimensions to represent that. Okay, so say you've got f of x, where x is your variable. You need to have your variable, say, going horizontally, and then your height above that axis will be your f of x. Okay, so that's where we get our curve. So we need two dimensions to represent that. If we've got two variables, we need three dimensions to represent that visually, okay? So if you've got a function f of x and y, if we set our z coordinate to be that f of xy, then when we draw this, we're going to end up with a surface. So the height of that surface at any particular combination of x and y is going to be our z coordinate, and that is just the function value at that x and y. Okay, so z is equal to f of xy. We can also represent this using things called level curves. And I'm sure that you would have met level curves before, but not thought about them maybe mathematically. All they are is taking a particular value of our function, so a particular height above that surface. So, sorry, we have a flat surface, and then we have our function surface, and we want to take a particular height. And we can take different values of those heights by setting our function f of xy equal to just some constant. Okay, and that will give, because our f of xy is equal to z, if we set z to be a constant, then it's going to be a particular height. So we do that, and we can represent our surface in two dimensions as here a set of concentric circles. and we write down what the value is of the function on that particular circle, okay? So have you guys met these things in real life, but not realized they're mathematical functions? Any ideas of where you'd see these? Anyone go hiking and look at a map? The contours on a map, right? This is just what contours are. They're just saying what is the height above sea level, and you draw a curve, a closed curve, usually of where, for a particular height value, you draw a closed curve that describes how far above sea level you are. We met it at the beginning with isotherms, okay? So if you have a look at a temperature map, and you also see things like this in a weather context for constant levels of pressure, so isobars. If you have a look at a weather map, these things are very common. It's because it's easier to represent these things in 2D rather than representing them in 3D and trying to look at a surface, because then you have to manipulate it and move it around, okay? So this is a little bit similar to projections in a sense, because we're trying to project data down from 3 dimensions down to 2 dimensions. Mathematically, we're just setting our function to be a particular value that we choose a constant, and that is where we get our level curves. Think of them as contours, okay? So I went through an example of how we can draw these. So if you have a function, you just set that function equal to some constant k, and then you can vary that k, and that will give you different level curves. In this case, for this function, it's just different straight lines with different intercepts. And here we had the equation for a circle, x squared plus y squared is some constant. Again, we can change what that constant is, and we get different level curves for that. In other words, different circles with different radii. Okay, the last thing that was in the pre-lecture material was talking about domains and range. As we're not going to be super notation focused here, the key thing to really remember is a domain is essentially all the sensible values that you can put in, and the range is all the sensible things that come out. Okay, so domain is things going in that make sense. Range is everything that can come out of it that makes sense. So in this example here, we know that you can't divide by 2. Can't divide by when x is equal to 2 because you have the denominator equal to 0. So we know that we can exclude 2, x is equal to 2 from this domain, okay? So we know that x can't be equal to 2. And on the top, we know that we can't have this being negative if we want this to be real valued. So we need to make sure that y is greater than or equal to minus x minus 1 to ensure that we don't have something negative on the top. So we can then represent that visually as being the domain of this function is this green shaded area with the exclusion of this vertical line here, what x is equal to 2. Okay, so that's a way we can think about representing them. We can find out what conditions our function can take in, and then we can represent that visually. The range is a little bit more complicated to work out. So the domain is fairly straightforward to do. The range is a bit more complicated. We would have to pick values of our x's and y's to see what possible outcomes we can get. So in this example here, I know that this thing on the top can take any value from 0 up to infinity. But if I change the value in the bottom, so if I set x minus 2 to be something positive, then it's going to be 0 to infinity. If I set x minus 2 to be something negative, then it's going to go from minus infinity to 0. So we can have any value. This function can produce any value from negative infinity to positive infinity. So that's just the real numbers. So I'm not going to quiz you too much on this kind of thing. Okay, it might come up on the OQs. It's not something that I want you guys to obsess about. It's something that you should be aware of rather than it's going to be a focal point here. Okay, so what is the domain and range of a function? Be aware of what they are. It's not going to be a major thing that we're going to be doing lots of questions about there. Okay, any questions on the pre-lecture material? Okay, let's go through some problems. Okay, so it's Monday morning, everyone's tired. Let's get you guys waking up. So for each of these functions here to start with, I just want you to shout out how many variables we have. So this first one, how many variables do we have? 3. Okay, so we've got 1, 2, 3. Someone say 1. 3 here. Okay, second one, how many variables? 1. Third one, how many variables? 2. Okay, the important thing here, although there's only x's on this right-hand side, it's a function we're told of x and y, so it's just the y doesn't appear on the right-hand side. This is a bit of a trick question, so I don't really like this one, actually. But it's a function of 2 variables because there are 2 things on the left-hand side. Number 4, 2, okay? Although there's an a on this right-hand side, that we would think of as a parameter, okay? So know the difference between a parameter and a variable. So x and y, they're variables because we're told on the left-hand side that h is a function of x and y. So x and y can vary. It's not told, we're not told that h is a function of a. So a is just a fixed parameter. So know the difference between a variable and a parameter. Okay, I'll skip over the next bit. Give examples of a function of 3 variables. You know, that's anything essentially, for example, f of x, y, z could be x plus y plus z. Okay. Think of a second one in your own time. Okay, so we've got a function down here at the bottom, f of x, y is equal to 1 plus the square root of 4 minus y squared. How do we evaluate a function of more than one variable? Well, we want to evaluate f when x is 3 and y is 1. Just like we would do of a function of one variable, we just substitute the values in. Okay, so f of 3, 1 is going to be 1 plus root 4 minus 1 squared. There's no x in here, that's why it's confusing. Okay, so x doesn't actually appear on this right-hand side, which is what threw me then. So you've got 1 plus 4 minus 1 squared, so 1 plus root 3. Okay, so we just substitute our values in. In this case, there wasn't actually any x value. Find the domain of f. Okay, so like I said, we're not going to be talking too much about domains and ranges, but just to go through an example of how you would calculate it. So because we want this to be real valued, we'll talk a little bit later in this course about complex numbers when we talk about eigenvalues in dynamical systems. Real numbers are basically everything that you've met up until now. We don't want the square root to be negative, okay? So we can't take the square root of a negative number and get a real valued number. So we know that this 4 minus y squared has to be greater than or equal to 0 for us to get sensible values out. So we can rearrange this. We put the y squared on the other side. So we've got 4 has to be greater than or equal to y squared. So it tells me that y squared has to be between, y has to be between minus 2 and 2. Okay, so our domain here is going to be all values of x and y where y is between minus 2 and 2. So there's no constraint on x here. X could be anything. Part of the reason why is because x doesn't appear at all here. But y has to be between minus 2 and 2 to make for this to make sense. What about the range? Well, remember the range is all the sensible outputs that we can get. So the only thing that's varying is the thing that's under the square root here. So what can we tell about that? So we know that 4 minus y squared, well, if y squared is equal to 0, in other words, if y is equal to 0, this is going to be at its maximum. If y is equal to plus or minus 2, it's going to be at its minimum because the square root of the thing under the square root is going to be equal to 0. So this has to go between 0 and 4. So this 4 minus y squared can only go between 0 and 4. So what does that tell me? That tells me that this function, remember we've got this 1 out the front, the 4 minus y squared square rooted has to go between 0 and 2. We're going to add 1 onto that. So this function has to go between 1 and 3. Okay, so To work out the domain, we just need to think about the sensible things that we can plug in. To work out the range, we need to figure out what is the possible set of outcomes that we can get. Okay, let's think about some slightly more interesting examples. So suppose we've got, there we go. Suppose you have a temperature humidity index. So the actual apparent temperature is both a function of the actual temperature as well as the humidity. This is obviously quite an important thing in particularly tropical latitudes. It's related to health, right? So you'll find that just because it's hot doesn't mean people die. It's hot plus humidity will make things a lot worse. Okay, so thinking about how temperature combines with humidity is quite important from a public health perspective. Here, we've got a table of different values for humidity and for temperature. If you want to find out what is the value of our apparent temperature, sorry, when is our apparent temperature 93 for what value of the actual temperature given a humidity of 40%, we just look at where is our 40% humidity. We read this like any table we would, so we want to look down here. Where do we find our apparent temperature is 93? It's when our actual temperature is 90. This in Fahrenheit. Do Canadians use Fahrenheit or do you use sensible? Celsius, you're sensible, okay, right. Sorry, American. Are there any Americans here? Yeah, sorry, but you guys are weird. Nobody uses Fahrenheit. Okay. Actually, I lied. The British media are really weird. So they teach, the British media, they'll talk about temperatures in Celsius when it's cold. So they'll be like, oh, it's sub-zero. When it's hot, they'll be like, oh, it's up in the 90s. So there's this invisible line where in the British media, they change from Celsius to Fahrenheit. So in fairness, we're even weirder. Inconsistency. Okay, so we've worked out that this 93, it'll feel like 93 degrees Fahrenheit when it is 90 degrees Fahrenheit and you have a relative humidity of 40%, okay? The next parts here, these are word problems here at the moment for us. We'll talk about things called partial derivatives and how we would actually work these out later this week. Here we're asked, how is the perceived air temperature, so this perceived air temperature is our I here, how is this changing when our T is 80, so when our temperature is 80, and the humidity is increasing? So that's saying, how is this increasing as we go along this road here? Well, in words, we can see that roughly it's going up by 1 or 2 degrees for every 10% increase in humidity, okay? So that's all I'm looking for here, right? I is increasing by 1 to 2 units, or 1 to 2 degrees, for every 10% increase in H. So how does that compare when the temperature is 100 down here? Well, now we can see that the apparent temperature is going up by, well, here it's 5 units from here to here. Here, at much higher humidities, it's 12. Okay, so we see that it's going up faster when the actual air temperature is higher as humidity increases. Okay, so there's this synergistic effect going on. Okay, so when the temperature was 80, the actual temperature was 80, increase of 10% humidity is causing roughly a 1 to 2 unit change in temperature, whereas when the temperature is 100 degrees Fahrenheit, a 10% increase in humidity is causing somewhere between 5 and 12 units of increase in temperature, okay? So this is, again, something you guys should be comfortable doing, is taking a table like this and interpreting it in words, okay? So what does it actually mean? You know, how would you explain this to your gran or your granddad or someone who maybe is not familiar with looking at tables and data? Maybe they are, maybe they're more familiar than you guys might be. Okay. Another way we can think about functions is in an evolutionary sense. So we often write down, or you might collect data, say, on a species and look at some of its traits or characteristics. and how that might affect its evolutionary fitness, okay? So the greater its fitness is, the more likely it is to reproduce and survive, pass its genes on to the next generation. So here, this particular study was measuring two things: the reversals of direction as this garter snake flees from predators, as well as how striky it was. And they plotted the data that they had, and they were able to fit this function to it. Okay, so we'll talk a little bit later in this course as well about fitting data. We'll do it in a simpler case. So we're just fitting, say, a line to use some data, but you can do that in more than one dimension. So that's where all of these different numbers have come from. They fitted based on these traits R and S. They've fitted their data to those traits, and they've come up with this surface. Okay, so this is just some surface. Remember, if we have our f of x, y, here we've got r's and s's, equal to z, that's just going to describe a surface. So it's just the same here. This is describing some surface. We've got some quadratic terms in here. So what we're asked is, if we've got two snakes, one has r is equal to 3 and s is equal to 1, so just particular combination trait values, and one with r is equal to 1 and s is equal to 3, which is most likely to survive? Well, all we need to do is plug these values in. Okay, so for the first one, r is 3 and s is 1. So what do? We plug these values in, so you can have 4.2 plus 0.08 times by r, and our r was 3, plus 0.102 times by 1, plus, and so on. Okay, if you do that, in this case, you get 3.64. The actual value doesn't matter too much. What matters is the relative value compared to the other one. The other one, if you plug those in, you get 3.42. Okay. Like I said, the actual values themselves don't really matter too much. What matters here is the relative values. So the first snake has a higher fitness, so this is the one that's more likely to survive in this case. Depends how you measure fitness. You might measure it in terms of reproduction. You might measure it in terms of survival. Obviously, there has to be a reproduction element. There's no point surviving if you're not going to reproduce. But for the purposes of this question, we're just interested in survival. Okay, so if we have some measure of fitness and we say, okay, we've gone out and measured different snakes, we've fitted a surface to this to estimate what their fitness is, we can then say, okay, what about some other hypothetical snakes? How might they do? Okay, so that's just a case of substituting some values in and looking at them. We'll talk a little bit about, in some of the later classes, about ways in which we can approximate fitness surfaces, and also thinking about the rate of change. So the rate of change is going to be really important when we're thinking about it. Okay, but we can think about them just in terms of plugging values in as well. Okay, the next questions here in the problem cast are all about graphs. I'm going to skip over those for now and come back to them if we have time. So I want to focus on the more biological ones. Okay, so here we've got some level curves. So these are our isothermals that were mentioned in the pre-lecture, but here for water temperature rather than air temperature. Okay, so we've got some depth of our water, and then we've got time, so a particular day of year. We can represent these things as a surface, and we can project down level curves onto a 2D plane. So this one here, for example, following this level curve, is saying anywhere along that, the temperature of the water is going to be 20 degrees Celsius. Anywhere along this one, it's going to be 12 degrees Celsius. Okay. So what we're asked here is, can we estimate the temperature on day 160 and the temperature on day 180 at depths of 10 meters and 5 meters respectively? Okay. So have a think about how you go about doing that. I'll walk around and answer any questions you might have. Okay, let's see what you guys think. So we've got limited information here, right? Whenever we're projecting level curves down, we're losing some of the information, right? We don't know what's going on between our level curves. If we're told we want to work out what is the temperature on day 160. The first thing we need to do is draw an imaginary line here, day 160, a depth of 10 meters. We go along here. So let's zoom in here. So we want to know what is the temperature of our water here. Well, it's somewhere between 8 and 12 degrees Celsius, right? It has to be between these two things because this is where our level curves are. Again, think of this if you find temperature difficult, think about I like to think about walking along a hillside and you've got a height of 8 meters and a height of 12 meters, and there's somewhere between those two things, right? So it's a little bit closer, maybe to, if I draw these a bit straighter, it's a little bit closer to 12. So maybe you'd approximate that T, day 160, depth of 10 meters is maybe going to be something like 11 degrees C. You may have a different answer, right? It might be 10, but it's got to be something reasonable, right? You wouldn't pick 8, you wouldn't pick 12, or outside of those bounds, right? How about on a different day? So day 180. Now we draw a dotted line here, and we want a depth of 5 meters. So this one is pretty close to that 20. So here, it's got to be between 16 and 20. So I would say in this case, maybe it's 19, maybe it's 19 and a half. The point is you can make an estimate based on these level curves, okay? So you should be able to look at some level curves like this and estimate a value between those level curves. Okay, let's think of another example with level curves. This time, you've got, we're not told what these are. Let's assume that these are heights. Okay, heights above or below sea level, okay? And you're going to follow this path here given by this green trajectory. So you start up here, you're going to follow this green trajectory. What this question is asking is, describe in words how this function is behaving. So I'd actually prefer to describe it biologically. So imagine you are taking a walk along this path, describe what is happening, okay? So if we're going, let's ignore the second part of it and just work from here through to P. Again, have a chat with your neighbor for a minute or so and just describe what you think is happening to this function, okay? Okay, so suppose you're starting off at this point here. I'm going to call it S. Can someone tell me what's happening as you travel from S to P? Imagine you're walking along a hillside. So what's going on to your height? Yeah? So you're going downhill. It's pretty simple. So you could say, okay, you start at somewhere above 18 meters above sea level. If this is in 18, or sorry, if this is in meters. Monday mornings, man. Okay, so you can also think about how steep the gradient is, okay? So it starts off, well, there's quite a big gap between the 18 and the 16, right? So that tells me that the gradient here is relatively shallow. Then the gradient gets steeper. So the hillside starts getting steeper as these curves get closer and closer together. So if you ever look at a topological map, you'll see that when you look at a relatively flat area that's maybe slightly rolling hills, you'll see that you've got contours, but they tend to be quite far apart. If you've got a very steep mountainside, then those contours are going to be very close together, okay? So the fact that these ones here are close together tells me that there's a steep section, or a relatively steep section, whereas these ones here are quite far apart, so that bit's more gradual. So you start off going downhill fairly gradually. It starts getting steeper, and then eventually, when you go below 12 meters, it starts leveling out again. And it's pretty gradual slope as we go between 10 and 8 meters, okay? So if you want to just give a really full description, you can say we're going downhill. You can say we're going downhill. We start at a height above 18 meters. We don't actually know what height we are. We can pretty guess because these contours, most of them are going up in 2, so 8, 10, 12, and so on, although that's not always the case. Oh, no, that is the case. We've got a 6 and a 4, 2. and so on. So they all go up in 2s. So you can pretty guess that we start off at height between 18 and 20 meters because there's no 20 on here. So we pretty start at a height between 18 and 20 meters. We end up at height 8 meters, and you can describe how you vary, how the gradient varies as you go along that trajectory, okay? Okay, let's go back and think about some level curves. So I'll do the first one of these, and then only got is to do the second one. Okay, so we're asked to draw some level curves. We've just been thinking about how we can interpret level curves. Now we're going to draw some of our own. So we're given a function here, f of xy is y minus x squared. We're going to draw some level curves. So how do we do that? For our level curves, we're going to want to take our function and we set it to a particular value, k, where k is just some constant. So that means I need y minus x squared to equal k. We can rearrange this to just be y is equal to k plus x squared. We just rearrange things in terms of y because it's easier to graph these things. Y is equal to something. Now I can draw my axes. And I just pick different values of k. So when k is 0, we've got y is equal to x squared. So that's just a quadratic parabola that looks like this. So this is my k is equal to 0. K is just going to give me my intercept with the y-axis. So when k is equal to 1, it's going to look something like this. And when k is minus 1, it'll look something like this. If I draw my 0s and my 1s on here, and my minus 1, it'll look something like that. Okay, so you just set your function equal to that constant, do a little bit of rearranging, and then see what you end up with. Okay, so have a go for the last few minutes at drawing some level curves for this function here. Okay, I'll give you a hint. If you write this as this is equal to k, think about what happens when you square both sides. Okay, again, I'll walk around and answer any questions you guys might have. Okay, let's see how you guys got on. So as above, we want to set our function f of xy equal to some constant k. So that's all I've done here so far. Do a bit of rearranging. So if we square both sides, we're going to get 4 minus x squared minus y squared is k squared. And then if I put the x and y on one side and everything else on the other, I'm going to get x squared plus y squared is equal to 4 minus k squared. Okay, so can anyone tell me what this is the equation of? Circle, yeah. So it's a little bit confusing, right? Because this bit here is not written as one thing, right? But this is just our radius squared. Yes. So I didn't have to write it in this form here, but we just typically write the equation for a circle as x squared plus y squared is equal to the radius squared. So it's just convention that people tend to write it in that form, whereas here, if you want to plot most other curves, you do y is equal to something, right? Yeah.
You were having a Monday morning, just factored out like 2x squared and y squared out of the roots. Is that something you could do or no?
You can do. I mean, as long as what you're doing is mathematically correct, you know, to follow up with this question here, there's nothing wrong with writing this as a y is equal to something, right? You could write it as x is equal to something, just as above, I could write this as x is equal to blah, 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 right? And then it would still give me the same curves. It's just what is the easiest thing to think about. So the reason I wrote it in this form here as x squared plus y squared is equal to something is because now I can just change this value of k and I'll get different radii. So yeah, you could do it in different ways, but for me, like this is the easiest way to think about it for this particular problem. Okay, so let's think about different values of k then. So if k is equal to say 2, then we can have 4 minus 4 squared, sorry, 4 minus 2 squared, which is 4. So 4 minus 4, which is 0. So when k is equal to 2, we actually just have a point. So our level curve is just a point here at 0. When k is equal to 0, then our r squared is going to equal 4. So our radius is going to be 2. So it's not very good. Circle, but that is supposed to be a circle. So when k is equal to 0, we have a circle of radius 2. So it goes through here, 2, 2, minus 2, minus 2. And then we could think about some other values. So for example, if k is equal to the square root of 3, then k squared is going to be 3. So we're going to have 4 minus 1, sorry, yeah, 4 minus 3, which is 1. I'm having a Monday morning. This one that goes through 1 minus 1 and so on, 1, 1, minus 1 is when k is equal to root 3. Okay, so again, this is not going to be a massive amount of, I'm not going to focus on lots of questions on getting you guys to draw, here's a function, draw it, right? But it's something you guys should be familiar with and be able to do, okay? Yeah. That's it for today. I'll see you on Wednesday.